I'm Diana Zigterman. I'm doing a presentation on ChromiumOS USB-C, specifically USB Type-C connections in the embedded controller. So for our talk today, first we're going to go over the Type-C specification, followed by the power delivery specification, which is a specification that kind of sits on top of the Type-C connection. And then we'll go over our ChromiumOS Embedded Controller TCPMv2 stack, which is our implementation of these two specifications. So first, for our USB Type-C specification, this is a general industry specification for anything that's using a Type-C port. It's available publicly on usb.org if you're curious. So Type-C uses a lot of jargon. So before every section, I'm going to have just a little table of what jargon we're going to be using a lot in this particular section for you to kind of get used to it. So the first one for here is sync. That is your port partner on the connection, which is consuming power. So for example, when your phone is charging, your phone is being a sink. When you have a USB stick plugged in, your USB stick is a sink. Source is the other side. So that's the port partner that is supplying power on the connection. So with your phone plugged in charging, it's probably the wall charger. If you have a hub or a USB stick plugged into your Chromebook, then the Chromebook is the one acting as the source in that connection. We're going to use the term VBus a lot. This is the voltage provided from the source to the sink for the sink's power. This voltage can be something like 5 volts if you have a flash drive plugged in. If your phone is charging, it's probably closer to 9 volts. If you're charging a Chromebook, it's probably about 20 volts. And then we have another voltage we're also going to talk a lot about called VCON. So this is an optional voltage that you provide to a powered cable. So an easy way to try and distinguish it from VBus in your mind might be to think of it as a connection voltage. This one will always be 5 volts, and it'll be significantly lower power because it's just for that cable to use. So diving in, this is a diagram of what your USB Type-C receptacle looks like on, for example, your Chromebook. It's got 24 pins, and as you know from using USB Type-C, it's completely flippable, and the pins are designed to support that, so you don't have to fumble trying to find the right orientation for it like you might have with a USB-A drive. So we're going to start from the middle out. First, we have D+ and D-. These are pins available for USB 2.0 functionality. If you're something like a USB 2.0 USB drive, then you only have to connect either D+ or D- on A6, A7 or B6, B7. And then the host will actually short the other two pins together to support you being in either orientation. Moving out from that center, we have CC1 and CC2. These are the configuration channels, and we're going to be talking about them a lot today because they are involved in how we set up our Type-C connections to begin with and how we put power delivery on top of that Type-C connection. These are also what are going to have VCON on them, if that's the connection voltage we talked about earlier for powered cables. And you'll see again, there's 2 of them in order to support cable flipping. Up next, we've got SBU lines. These are sideband usage lines. So these are available for things like alternate modes to take advantage of. So if you're running a monitor on your Type-C connection, the DisplayPort alternate mode that it uses, it will be using these SBU lines. Also, if you use USB 4, these are used in the USB 4 connection. And on our Chromebook specifically, we use the SBU lines for our debugging. So if you've used a Servo V4 or a SUSY Q plugged into your Chromebook, these SBU lines are how you're getting your consoles out from your Chromebook. Moving outward, we've got the VBus pins. So this is that USB bus power that might be 5 volts, 9 volts, 20 volts, something like that. It's going over these pins. You'll notice there's a lot more of these pins than there are of the CC pins. That's because we're going to be delivering a lot more current over VBus than we will over VCON, which is much lower power. And moving out from them, we have the TX and RX pairs. These are available for USB 3.2 superspeed and USB 4. There's 2 sets of them, so a device can implement either a single lane configuration or it can implement a dual lane configuration. And then on both the host and the device side, they'll usually have muxes and detection to direct the lines accordingly based on what orientation was plugged in. So as we move into the rest of this talk, we're mostly going to focus on these yellow connections, the CC1, CC2, because we're going to use those to build up our base connection and add power delivery on top of that. So this is what it looks like when you start a USB-C connection. So your source, so your charger or your Chromebook, will present a pull-up resistor called RP on its CC line. So a pull-up resistor, if you don't do a lot of electronics, is just a resistor that's connecting to a higher voltage. So it'll bring anything that connects to it up to a higher voltage. There's 3 different RP values you can have that'll indicate the current your partner is allowed to draw. There's default USB, which is 500 milliamps, 1.5 amps, or 3 amps. On the other side, the sink side, the power consumers, they're going to present a pull-down resistor called RD. So the pull-down resistor is connected to ground, and it'll pull down the voltage of whatever's associated with it, or whatever's connected to it. So a dual rule device, which your Chromebook generally is when it's turned on, it can supply power or it can consume power, and it'll actually toggle between presenting these 2 different resistors. We also have powered cables, the ones that require VCON that I mentioned earlier. These will present a pull-down value called RA on their CC line. If you look at the diagram on the right, you can see our source has pull-up resistors to RP through both connections. The cable is going to take one of these RP resistors and connect it through to RD on the sink side. And then the other resistor, the other side will either be open if the cable does not need power, or it'll present an RA if the cable does need power. And the RA can connect to both sides, but it does not connect through the cable. So some examples of what this looks like physically. This is a graph, a voltage versus time graph of what it looks like on your Chromebook when it's just sitting, turned on, and it's toggling. So these high points are our dual role port presenting RP. So this is us saying we can source, we're ready to connect to any sink that connects to us, and it's about 3 volts. These low points are us presenting RD. It's about 0 volts, and that's moments where we're saying we can connect to a source if a source is connected. And we're just going to sit and toggle back and forth doing these until someone connects. So at the end of the graph, you actually see what it looks like when a sink connects. So this is a sink device connecting. You can see we start bringing our voltage back up to that RP value, but it ends up lower because the RD pull down on the other side is bringing the ultimate voltage lower over like a voltage divider. If you're curious, this RP value in particular represents 1.5 amps. So we've connected and we've given the sink permission to pull 1.5 amps on the connection. So there's a few different combinations you can have from the source point of view. So if both your CC lines are open, nothing's attached. So that's if both lines are at that 3 volt value we showed. If you've got RD on one line, open on the other, that means you've got a sink, no powered cable involved. If you've got RA and open, you've got a powered cable, but no sink is attached yet. RDRA would be a sink with a powered cable. So a lot of these would be things like docks will often have powered cables with them. If you've got RDRD, that's a debug accessory. So that's something like if you have your Servo V4 connected to your Chromebook, we'll be presenting RDRD on the Servo V4 and detecting that as a debug accessory on the Chromebook. RARA is audio accessory. So once we've gotten these connections through, there's actually one tricky thing that we do as a dual role device. So we can change our CC termination at the beginning of that connection to try to assert ourselves as the source or the sink. In our case, we prefer to try source, or we want to be the source as often as possible. So we'll do some little changes on the CC terminations to see if the partner will let us source. A lot of things like a hub will then turn over sourcing to you and let you be the source. Something like a charger will never do this. So the try source will fail and we'll just go into being a sink. We do that in order to make sure, like, for example, if you plug your phone into your Chromebook, you would expect your Chromebook to charge their phone, not vice versa. Once we've gotten this attached, everything's debounced and everything's stable. We're going to enter into the attached state as either the source or the sink. If we're the attached source, it's our duty to provide 5 volts on VBus, and we may be providing 5 volts on VCON if there's a powered cable, so if we have RA present on the other CC pin. And our job will be to sit and monitor the CC lines to know when the sink detaches. So if you think about our voltage graph we saw previously, when we're connected, that voltage will be closer to about 1 volt. And when the sink detaches, it'll bounce up to 3 volts and we'll know the sink has been removed and the connection is terminated. If we are a sink, we are allowed to start consuming power up to the RP advertised current. So in that graph we looked at previously, that'd be 1.5 amps. And our job as the sink is to monitor the VBus level to know when the source has unplugged from us. So once we're attached, we've got a few different roles that we consider the port to have. So the power role represents who is supplying a VBus, who is giving power to the other port partner. The data role represents who is the host of this connection. The vcon role represents who is the one supplying vcon to the RA pin on the cable. And anytime we don't have USB power delivery, these roles are fixed for the whole lifetime of the connection. So for example, if you've got a USB stick plugged into your Chromebook is always going to be the source DFP vcon source of that connection. The USB stick will always be the sync UFP, not vcon source of that connection. And we're going to get into the data role more specifically in the next session. So this is exactly what you can get with your Type-C connection. You can get your resistors set up on the CC line such that you get into this attached state with VBus being supplied. And once you're in that state, you can enter into power delivery. So power delivery is a separate specification, also available on USB.org. And everything we can do in power delivery happens once the Type-C has gotten into that attached source or attached sync state. So jargon for this section. I'm going to say PD a lot. It stands for power delivery. And that's the specification that's providing messaging on the Type-C connections and allows us to have a larger feature set and to be able to take more actions on those connections. DFP is a data role that I talked about from that previous slide. It stands for downstream facing port. So this is your port that's generally a USB host root port or a hub downstream port. So if you think about your Chromebook, its ports are always a host port. If you think about your Chromebook connecting to a hub, the hub is the downstream facing port to, for example, monitors attached to it. But for your Chromebook, it is the upstream facing port, UFP. So this is the port that's acting as a device. So the monitor attached to your hub would be the UFP to that hub. And the hub attached to your Chromebook would be the UFP to the Chromebook. And it kind of goes in a little chain like that. So once we're in this attached state, and we've already got our roles, source, DFP, vcon source, the sync will be UFP, not the vcon source, we are allowed to start PD contract negotiation. So all PD connections are going to start with this explicit contract negotiation. It's the little magic dance that we do in order to know that PD is available and working on our connection. So that CC line that we think about going through the cable, the one that connects RP to RD, is going to have messages going on it. So the messages can be simple commands. These are called control messages, or they can be more complex and have data with them, or those are referred to as data messages. So if you look at this diagram on the right, here we have the source port. As soon as we're attached, the source port's going to start sending out a data message called source capabilities, which is it saying, hello, here is my menu of available power options and some little facts about me. This will include things like whether it supports USB communication, whether it's something called unconstrained power, which would mean it's plugged into the wall and you can pull a lot of power from it. The source will be sending these out for about 5 to 10 seconds, because sometimes it takes the sync a while to boot up if it's something like a dongle that wasn't powered previously. So once the sync is powered and it's ready, it's going to receive that source capabilities message. It's going to run what's called a cyclic redundancy check on that message. And if the check comes through good, that means the message was error-free. And we're going to let the source port know that we're awake. We've seen this message. We're processing this message by sending it a good CRC message. So every message will have a message ID in it. This good CRC would have the same message ID as the source capabilities to let the source port know we've received the capabilities error-free and we're processing it now. These good CRCs are used all the time on PD communications. So from here on, they're just going to be little lines going back and forth that we use to just acknowledge every message as being received correctly, error-free. So the sync port's going to look at its menu of power options that it got from the source port, and it's going to decide what it wants. And it will put in a request. So it'll say, I like this voltage and current combination. I would like to start using that voltage and current combination, and it'll send it over to the source port, who will again good CRC to say that it got the message error-free. The source port decides to accept it. That's another control message, and it'll send an accept back to let it know more power is coming. Usually not in first contract negotiation, but sometimes later on it may send something like a wait if it's not ready to source power, or it might send a reject if it doesn't want to source that power. If that happened in an early contract negotiation, it would be required to go back and send a new source capabilities representing something the sync was actually allowed to draw so we could continue on with our contract. So in this case, it's accepted. And then it starts turning on its power supplies and getting ready to source out the current that it has promised to this port partner. Once that's done, it'll send a power supply ready to the sink. And at that point, we are in a PD contract. And once that's all in place, we're allowed to send a lot more different messages. So what exactly can we do with PD? So we can negotiate new PD contracts. These can go up to 100 watts. So if you're just on a Type-C connection, like we talked about in the first section, that's always going to be 5 volts. Highest current you can get is 3 amps, so that limits you to 15 watts. Once you have PD in play, you can negotiate 20 volts. You can negotiate 5 amps if you have a cable that's capable of supporting 5 amps, and you can get up to 100 watts. You're allowed to swap any of your roles. So those roles we talked about, the data role, the power role, the VCon role, you can swap all of those around based on what you need to do for your port. So for example, a dock will probably want to be the source, but it also needs to be the UFP. So it'll need to do some swapping to get itself into that configuration that it wants. You're allowed to gather information about your electronically marked cables attached to you. So that'd be, for example, if you have a cable that's going to support 5 amps for the 100 watt contract, or if you have a cable that's going to support something like Thunderbolt. You can enter into alternate modes. So that's how DisplayPort gets started up on your Type-C connection with your monitor, is that you'll be entering into DisplayPort alternate mode, setting up your muxes for that, using the SVU lines for it. You can set up USB 4 in the connection. You can actually probe manufacturer information from your port partner. So that'd be their vendor ID, their product ID, all kinds of information like that that can be helpful. You can retrieve battery information from your port partner if you want to know what their battery status is. And then we can also try and recover when we hit errors. So there's protocol errors, which are little messaging errors back and forth. Like, for example, if someone doesn't good CRC your message that you sent, that'd be a protocol error. So you can kind of soft reset, try and get the connection back into a good state. If you hit larger communication errors, like, for example, your soft reset fails, then we go into a hard reset, and that's actually just ripping out the entirety of what we did in PD and resetting it back to the default role state, everything default. We have to start a new explicit contract. And we only do that when there's an unrecoverable error, basically. So once we're in that PD contract, we can, our roles have taken on additional nuances, responsibilities, and privileges. So our power role, we're still the one who's supplying power to the sink port. However, we also have to be in control of collision avoidance and PD3.0, which is the most recent PD specification. So the collision avoidance is to help avoid when you have 2 messages going on the CC line at once and they get jumbled and neither message successfully goes through. So remember earlier we talked about how there were different RP values. Since during a PD contract, we don't need those RP values anymore to represent current because we have a source capability that had a more enumerated current value. We actually reuse those RP values in PD in order to indicate whether the sink is allowed to send a message. So we'll use RP30 to indicate it's okay for the sink to send a message, and we'll set RP15 to indicate it's not okay for it to send a message because the source is about to send a message. And that helps increase the integrity of our connection. So on the sink side, it's still consuming power, but then it has to watch that RP value to know when it's okay for it to send messages in PD3.0. For the data role, we talked about the DFP is the USB host. It is the one that gets to control alternate mode entry. So your Chromebook gets to decide when it enters the DisplayPort mode with a monitor. In PD2.0, it was also in charge of information gathering, so things like gathering vendor information from the port partner. In PD3.0, that was expanded to be allowed to be done by either port. The UFP will just be acting as a device. It'll be the one who enters modes when the DFP tells it to. The VCon role is still going to be the one who's supplying the VCon power to that electronically marked cable. So that'll be 5 volts. Even with PD, it's still 5 volts. Very little current, just whatever the cable needs in order to function. But the VCon source is also the only one who is allowed to communicate with the cable, to probe it for information, ask it if it can run 5 amps, ask it what alternate modes it might support. And the port partner whose VCon role is off is unable to do this. So physically speaking, what does it look like when we're, for example, swapping our roles around? These come in atomic message sequences, or AMSs. So these will be sequences of messages that are defined in the PD specification. There's a lot of them. Some of them are interruptible. So for example, if you're asking for vendor information out of a cable or a port partner, that's viewed as low priority, and the port partner can interrupt it with whatever they want for something else. Most of them are not interruptible. So something like negotiating a new power contract, you can't interrupt it. And if you send something unrelated to that AMS during the course of it, we have to go back and reset. That would be a soft reset. Unless power is transitioning, in which case it would be a hard reset. So many of them are only 2 messages. There'll be ones where they say, hey, give me your sync capabilities, done. Some of them are more complex, like the power negotiation we showed earlier has got 4 messages going back and forth with careful timings. And then any protocol error in your AMS is going to cause a soft reset. So if you send an unrelated message, if suddenly you're not getting good CRCs back, and that's going to cause both of us to reset our messaging layers. So we will reset like our message ID counters that we use to track for duplicate messages and to send good CRCs. And we'll reset ourselves back into a state of trying to get back to good communication. So an example of what atomic message sequences would look like. So in this example, there's a sync port. And the sync port decides, I would like to become the vcon source. So it's going to send a control message called vcon swap over to the source port. And the source port will accept that. It'll say, okay, I'm going to yield my vcon sourcing to you. And once that's done, the sync port can turn on its vcon sourcing, and it'll send a control message of power supply ready to the source port to let it know that it can stop sourcing vcon. So vcon is a make before you break connection, which means that both sides will source vcon for a little while until the power supply ready comes through, and then the source port can stop sourcing vcon because we don't want to remove power from the cable while it's in operation. So at that dotted line, that's the end of an AMS. So this was a 3-message AMS. It's not interruptible. So if the port partner had tried replying to the vcon swap with something like, let me know your manufacturer information, that would have been an error and we would have had to go through some resets. And then under the dotted line, we're going to start a new atomic message sequence. This one's going to be with the cable. So the first thing we're going to do talking to the cable after vcon swap will always be a soft reset. So that's us saying, let's get in sync for messaging. Let's make sure we've got our layers synchronized together. We've reset our message ID counters, all that. The cable will send back an accept once it has performed those actions and it's ready to communicate. So that's basically a summary of all the high-level things you can do with PD. And now we're going to dive into our implementation, our ChromiumOS EC Type-C Port Manager version 2 implementation. So jargon for this section, TCPM. This is a Type-C port manager. So it's going to be in charge of managing the state of our USBC connection. It's going to decide what PD messages that get sent, and all of this code will be running our embedded controller chip. If you've been in other sessions, I'm sure you've heard about the embedded controller chip. It sits on the board. It will talk to things like sensors, the lid sensor. It'll power on the SoC. And it's one of its other jobs is to be the Type-C port manager. TCPC, which is one letter off, so it can get a little confusing, is the Type-C port controller. So in our architecture, this will be controlling the physical communications on the CC line. So it's going to set our CC termination voltages. It's going to report the voltages that it sees on its line, and it'll be sending and receiving PD messages for us. They also take care of the good CRCs for us. Often on Chromebooks, this is a separate physical chip. Sometimes it'll be embedded into the embedded controller, but usually it's a separate chip located by the port. PPC is a power path controller. It's an optional separate chip, which will control syncing and sourcing VBus. It'll have extra features in it to prevent shorts, under voltage, over voltage. It'll report to us if we've got an overcurrent event that's happened. And then last, we have our USB MUX, so our Universal Serial Bus Multiplexer. So this is always separate from the EC, but sometimes it's integrated into a TCPC. Its job is going to be to detect signals, to direct all the signals and pins to the correct places on the SoC for USB and DisplayPort. And it'll also be handling the flipping polarity, making sure it's getting the lanes going in the right direction for that. So the first thing I always ask when someone tells me that they're talking about V2 of something is, what happened to V1? So our TCPMv2 stack was written a long time ago in 2014, back in the earlier days of PD. And it was written as one giant state machine that was in a single file that kept growing. The link is here on the, or a pointer to the file is here if you're interested in looking it up in our public code base. But it was basically trying to do everything in one file, and the design became very difficult to match up to the expectations from the specification, and very difficult to add new features to for PD3.0 when PD3.0 came out. So we created TCPMv2. This is our TCPMv2 PD task. You can also look it up in our public code base if you'd like. It's in common USBC in the EC platform code base. So TCPMv1 had this 1700 line while loop with a giant switch statement in it. And we've replaced that all out for 3 state machine calls. These state machines are actually defined in the specifications we talked about earlier. And we're just implementing those state machines in our code, and they're separated out accordingly. So it's also designed so the type C state machine can run independently. If for some reason you had a connection where you wanted only the type C connection and no PD capabilities on top of it. And boards can choose the appropriate policy engine and TC state machine to run. So for example, a Chromebook is always going to run DRP. We pretty much just have code to support DRP and charge through VCon powered devices right now. But the infrastructure is set up so we can support any number of different state machines that we need to. So if we look more closely at the layers, on the top we have the policy engine, the PE. All these states for this engine are defined in the USB PD specification. Its general thing that it does is it'll direct and it'll respond to PD messages. The protocol layer is also defined in the USB PD specification, and it's going to be composing these PD messages. It'll be putting headers on them. It'll be coordinating the sending and receiving of them. There's something in PD3.0 called chunked messages. It'll be taking chunks of messages and compiling them into one big message when we need to. So it'll handle all the nitty-gritty of the message details. And then below it, we've got the Type-C layer. So this is from the USB Type-C specification, and this layer is in charge of everything we talked about in the first section of this talk. It'll handle all the aspects of initial connection on the CC lines. It'll handle sourcing VBus. It'll monitor for disconnection to know when we're physically disconnected from our port partner. So how do these interact together? We've got a lot going on in this, but we'll start talking about our TC layer. So the TC layer is going to be implementing that connection we talked about earlier. So it'll be talking to the TCPC in order to let it know what CC voltages or what CC resistors we need to be setting right now based on what power roll we want to be. And then they'll be getting those voltage levels back from it in order to detect when we have a port partner connected. Once we have something connected, the TC is also going to be communicating with the PPC in order to source out VBus and VCon, or sync in VBus if we need to. And it'll be talking to the USB muxes to let it know what data roll we are and have it arrange its lines accordingly. Once we've gotten into that attached source or attached sync state that we talked about in section 1, it's going to enable the PRL and the PE layers. So all these layers are going to talk to each other using atomic flags, and we'll give you some examples of what kinds of things they'll be doing by revisiting our VCon swap AMS that we talked about earlier. So for the VCon swap AMS, it would be the policy engine's decision to say, you know what, I would like to be VCon source. It would put together this information and set a flag for the PRL to let it know, hello, I would like for you to put together this packet proposing a VCon swap to the port partner. The PRL is going to be the one who interacts with our TCPC to let it know that we have a message we want to send. The TCPC itself is going to take care of validating that good CRC. And when it does, it'll tell the PRL it was successfully sent, and then the PRL will let the PE know it was successfully sent. And then we wait for a response. We get the response from the TCPC to the PRL to the PE. When it gets that accept, the PE would then tell the Type-C layer, hey, I would like to turn on VCon now because I have permission to turn on VCon. The Type-C layer will turn on VCon, and then it will notify the policy engine layer when VCon has been turned on, so we can create that power supply ready message, tell the PRL to compose it, and then tell the TCPC to actually send it down the line. So just to give you an idea of a practical example of what happens for those. So that's a broad summary of our USBC stack. Here linked we have the public specifications for Type-C and power delivery. We also have a link to our ChromiumOS TCPMv2 code if you're interested in looking at the code. And then we also have a markdown file that has an overview of TCPMv2 with some of this material and then some more material talking about like the state machines in action themselves. So now I believe we are ready for questions. Awesome. Okay, USB-C and Thunderbolt 3 are the two most confusing ports to me right now. What is the difference between them, and are they supposed to be mutually compatible? So USB-C actually has support on it for Thunderbolt 3. So if you look in the Type-C specification, they've got an appendix added talking about how this works. Basically, when we're setting up a connection, we can probe manufacturer info from the other side, and it'll have things it'll have messages it can send us essentially saying, hey, I support Thunderbolt 3. I am able to provide Thunderbolt 3. And so from there, you can enter into Thunderbolt mode over your USB-C connection. So Thunderbolt 3 has kind of been subsumed into the Type-C connection. And as we move towards USB 4, it's especially been encompassed in that Type-C connection because we enter USB 4 over Type-C connections using in that case, just a straightforward data message that says enter USB 4. So if a laptop Chromebook is connected to an external monitor via USB-C and flickering, this is the behavior which indicates that the throughput required is too high. This will be dependent on what's happening on the system. It could be a UI problem. It could be a problem with the bandwidth that we set through. Like some things will be a hub plus a DisplayPort, which means we have half the lines available for DisplayPort and then the other half have to be available for USB. So it's hard to say without more data. Okay, it's been a pleasure talking to you. Bye.